I think there is no problem. You see my presentation well.
Yes, everything is okay.
Okay, thank you. So first of all, of course, I would like to thank organizers for giving this opportunity to me to give a talk organized by Ege University, which is very important for my career, and also for Istanbul University as well. So I also thank Ali Alpar. I think I'm one of the third generation researcher because my supervisor Yavuz, he was student of Ali Alpar, so I'm the third generation. But my talk will be mostly to fourth generation researchers, mostly to students, and this is the title of my talk and highlights from observations of X-ray binaries with Insight HXMT. So, but of course, I cannot give all the highlights obtained from Insight HXMT, but I can maybe introduce Insight HXMT to the people who would like to work on X-ray data, maybe who are not aware of there is a satellite called HXMT, which is quite hard to tell. So this is my outline, and first I will talk about X-ray binaries, since the sources that I will give as an example here are X-ray binaries. So there are two types of X-ray binaries, low mass and high mass X-ray binaries. Very briefly, I will give introduction of them, and I will spend most of my time to advertising Insight HXMTs then. So I will give a bit of history of that and what kind of equipments are located on the satellite and how data reduction is done, how can people obtain data from that, and I will give some output of Insight HXMT. And finally, I will also give an example which I have done, I have did by using Insight HXMT data. So this is my outline. But again, if you ask me how I would like to use this opportunity, I would like to use this opportunity. My aim is mostly that to encourage young generation to use Insight HXMT data and to collaborate with IHAP. IHAP is the Institute of High Energy Physics, in which Insight HXMT is operated from there. It's located in Beijing, China. So, and I will say just one word as final, and I will finish my talk then. So, low mass X-ray binaries are binary systems, of course, and we obtain X-ray from there. And they have one object is a compact object. It can be either black hole or a neutron star. It can be also white dwarf, but the name can be different then. So low as a name comes from the mass of the companion star. Okay, if the companion star is lower than, let's say, solar mass, there is no very restrict rule to distinguish high mass and low mass. So what we can just simply say solar mass. And the companion star is also called donor star because the matter comes from the companion star to neutron stars. The main accretion mechanism, main mass transfer mechanism of low mass X-ray binaries is Rochlop overflow. So there is a neutron star here or a black hole, and the other star, low mass star, and in its evolution, it fills its Rochlop, and from the first Lagrange point, it starts to transfer material to the Rochlop of the compact object. Since the companion star rotates and it has a spin, so the transferring material has angular momentum, then the material transferred to the Rochlop of the neutron star creates an accretion disk around the compact object. I say neutron star, but let's say compact object, instead of falling directly onto it. So, of course, the separation is important. There are some other quantities is important. But this is what it is there. So it creates an accretion disk. But what I'm interested in, not the source, but the inner layers of the disk and interaction between magnetic field of the neutron star and the inner layers of the disk. I will come to this later on these slides, in last slides actually, while I'm showing my output of Achilles 1, which is a member of low-mass X-ray binary population. So they are old systems. So 10 to the 7, 10 to the 9 years is the lifetime, and they observed in galactic disk, bulge, globular clusters. So this is also important. They have relatively low magnetic fields, 10 to the 8, 10 to the 10 Gauss. So it's very low. So as we know, neutron stars are born in supernovas. So they are born with the fastest spin of their entire life, and by losing angular momentum, they spins down. So from this, if we see any old object, we expect to have relatively lower spin. But we have seen some pulsars spinning with millisecond period. So they are old, but they spins very fast. So low-mass X-ray binaries can be possible incubators of millisecond pulsars, because the accreting matter does not just transfers matter, but also transfers angular momentum. So it spins up the star. This is quite known phenomena, and it's called recycling scenario. And when it comes to high-mass X-ray binaries, as I told in the previous slide, the high refers to the mass of the companion. Again, there is not a very strict rule. Some papers say it's 10 solar mass, some papers say it's 1 solar mass, but the main rule to distinguish these two classes are the accretion mechanism, let's say mass transfer mechanism. So the donor star is usually O and B type stars, or blue supergiants. And as you well know, this type of star has very strong stellar winds, as you can see from this illustration. I took it from ESA. So the accretion mechanism or mass transfer mechanism is this strong stellar winds from the companion, and they are relatively young, and so the lifetime is about 10 to 6 years, and they observed in Magellan Cloud, Open Cluster, and OB associations, etc. So the magnetic field is relatively higher than low-mass X-ray binaries. Okay, these are the stars that I would like to give some examples of observations taken by Insight HXMT. So now let's come to the Insight HXMT. It's very hard to tell for everyone if you are not aware of this, and if you didn't tell this word too many times to anyone. But we can also use this name of the satellite, Insight. So it's the first Chinese satellite, and it's funded on 2011, but the story stays far behind it, far past, and total weight is about 2.5 tons, and it's about 550 kilometers altitude with 43 degrees inclination. It's, let's say, it's circular orbit, but it's not exactly. There is 20 kilometers difference between aphelion and perihelion of the satellite. So it has 3 different modes. One of them is pointing mode, scanning mode. It scans the Milky Way, the disk of the Milky Way, and it also has GRB mode with enlarged the energy band. Okay, so it designed in 4 years and launched just before I went there to 2017, and I couldn't watch actually, and it's called Insight. So let's come to history of that. As you can guess, the X-ray missions are not started with directly satellites with that kind of technological stuff. It started with balloon flights. Maybe that balloons were very technological at that time, of course. And on to the 1970s and 80s. So China started X-ray missions with balloon experiments. And this is the announcement of the first proposal of high energy X-ray modulation telescope. So even 1994, China put an aim to observe, to send an X-ray satellite to observe very hard energy range, very high energy range, and with very high time resolution. The technical name tells us this. And it's funded in 1911 and it's launched. This is a picture from Jiuquan, China, when it is launched. Okay? And the name of Insight has very nice story, actually. I would like to tell this. I like to tell this. It's very romantic, or it's very poetic story. Actually, public decided to give her name to HXMT satellite. So there was an election on internet, and people decided to give the name of Hezhi Hui to the satellite. She is one of the most known particle physicists, and she was one of the first scientists who proposed China must send an X-ray satellite. So actually, she is also known Chinese Marie Curie. She's a very iconic person in China. So, and in Chinese, Yan, this character, and this is in pinyin, Yan means I. So they decided to give Hui Yan to HXMT. So still the Chinese name of HXMT is Hui Yan, which means the eye of Hui. So by giving this name, they represent their respect to Professor Hezhi Hui, and also they maybe show their respect to human as giving a human name to a satellite. And when you connect Hui and Yan together, it's not just meaning the eye of Hui, as you can guess, to give eye to a telescope, it's classic. But when you combine Hui Yan, it also means in Chinese, understanding deeply with all details by using your senses and by using your knowledge. So, which is insight. And that's why insight is the name of hard X-ray modulation, which is the technical name of the telescope. So if you are, if it's not easy to tell HXMT for you, you can simply call Insight to the satellite. Anyway, this was just a poetic story how the name comes from. But this is the mechanic behind it. So these are the payload on HXMT. There are three main detectors. So these are low energy detector. I will call LE after now. And it's sensitive to 1 to 15 kV with the effective area of something like 400 centimeters square. And this is ME, which is medium energy detectors. And of course, this is theoretical 1 to 15. When it comes to analyzing the data from there, you always use narrower energy band. So in my works, I mostly use 2 to 7 kV, 2 to 10 kV. And so let's come to ME then. It's sensitive to 5 to 30 kV. Again, in practice, it's between 7 to 25, etc. But the biggest advantage maybe of hard X-ray modulation telescope is the large effective area on high energy band, These detectors are called high energy detectors, HE, and it has the 5,000 centimeters square effective area, and these are the star trackers. So this is the effective area as a function of energy of Insight HXMT. Then here you see the advantage in high energy band. So this is a comparison between maybe well-known satellites by most of you, RXDE, which is dead right now, but I still use the data from there. Community still use the data from there, so it's still important. So again, a reminder for young generation, for the fourth generation of researchers of Turkey, then it's very important to start to use Insight HXMT data as RXDE tells us. So RXDE worked more than 20 years, and after even it's dead, we still use its data. So it's very good time to start in early stage of HXMT. So this is the comparison. Again, sorry, when it comes to detection area, HE has quite good advantage. Sorry. And also in time resolution of HE. So these are there is no, by the way, any imaging detector on that, so you don't see the image. Okay. Here is the view of LE, ME, and HE. It has two different field of views, small field of view and large field of view, it's called. And these are the area that HXMT sees, and these three detectors are these ones. Okay, so you can use only one of them, or you can use both of them, or you can use large field of view and obtaining something like circular area. But I mostly use small field of view to get more signal to noise ratio. This is just a recommendation if you will use any of the data from here. So there are, of course, some constraints actually which affected me a lot. So solar avoidance angle must be larger than 70 degrees to start an observation. And it passes South Atlantic anomaly in 15 minutes. Of course, while you are passing SAA, you have to switch the detectors off for 15 minutes. You cannot use it. So Earth occultation is about 30 minutes. So these are the constraints you have to take into account. But there are some, I will also show on the web page of the Insight HXMT, there are some engines. You can just type your source that you would like to observe, and it calculates all these quantities for you, and it gives if it is observable or not. So when it comes to data reduction, it's quite similar to RXT. This is, but of course, when we are talking about data reduction, first I have to tell how you can obtain the data from there. So this is the web page of IHAP, and this is the English web page of Insight HXMT, but Chinese web page can be more updated. It's not very hard to understand with pictures and formulas and graphs. And the software is HXMT soft. It can be also worked under HiaSoft. So you can install HXMT soft under HiaSoft, and you can somehow, it can be somehow embedded to each other. And this is the latest version, quite new. I think it's released in November. So it's always better to use the latest version of the software and latest version of the calibration, since still it's the early stage of the satellites. So if you have any problem, if you download the data and trying to install the software, you can directly ask me from email, or there is an expert list here. They are very motivated to answer your questions, so you can ask any person from this list. Okay, so mainly there are a few steps to obtain the final version of the data, final version of spectrum, background spectrum, response file, etc. I just give an example here on low energy detector, but it's very similar to medium energy detector and high energy detectors. So you have to pass all these steps. These are the tasks: LEPICAL, LERECON, LEGTIGEN, and it screens the data for the constraints that I show in previous slides. And finally, you get the second generation data. They call second generation. These are the first step data, and these are the second step data. So, and then finally you get light curve, spectrum, response file, and background file. Then you have everything to use in XSpec. Okay, and of course, if you need a barycentric correction for doing timing, there is HXBary. It's very similar to FXBary, which is used in HiaSoft. There's also HXBary 2, like FXBary 2. So you can use HXBary to screen data, and you can use your favorite program, Python, IDL, or any other program to do timing. Okay, so this is a schematic view of obtaining data. You use the first generation files. By using calibration, you get good time intervals, and you screen the data. So by screening the data, you can get light curve, background, spectrum, and response. There are lots of parameters of these steps, but actually I wrote pipelines to create spectra. When I'm in China, I wrote pipelines. So now it became very easy to obtain spectra, light curve, and by the way, HXMT software also has pipeline, but you cannot control everything if you use their pipeline. So let me introduce my pipeline here. So in this pipeline, you are controlling everything, all the parameters from these first steps to obtain spectrum, response file, background files, etc. Maybe I just need to update just a bit to make it work in this version. I don't remember if I did it, but it must be very easy to do. Maybe it can also work. I don't know. I haven't checked right now. So if you would like to use the data, and if you need a quick pipeline to obtain spectra, you can also ask me directly, and we can collaborate with you. I can send my pipelines to you. So it's open for you as well if any of you are very motivated to use HXMT data. Then, so these are the stars that observed up to November. So you see very famous black hole binaries, Cygnus X1, this one, and it's observed. So there's quite long list. So they observed, all these stars are observed. Okay. So also it covers the observation, it covers neutron star binaries, black hole binaries, some extragalactic objects, and some other kind of, because they also observe blank sky for calibration, and crab, they observe crab a lot, and the calibration team also uses crab to make better calibrations. So up to, yeah, 31st October of 22, 13 megaseconds exposure time black hole X-ray binaries are observed, and so 80% exposure time of bright sources and newly discovered outbursts, and also neutron star X-ray binaries And survey, as I said, there is also detector on HXMT for galactic disk survey. So some pulsars and they did timing, etc. So this is the exposure map. So it covers almost all visible sky. So this was Insight HXMT, and I would like to pass to what I actually did there. I also collaborated in many other papers, but this was led by me, and it was from early Insight HXMT state, very early Insight HXMT state. So first, I would like to introduce you one of the most known neutron star low mass X-ray binary, which is also accreting millisecond X-ray pulsar. I will come to that. It's a low mass X-ray binary. The quiescence luminosity in X-ray band can be this, and in outburst, it can reach up to 10 to 35 arc per second. So this is the long-term light curve of Aquila X1 obtained by ASM and MAXI. And this is the 2018 outburst in which we observed Aquila X1 as, with the pointing observational type, but we could only get 3 data. I will come to that again. So the orbital period is almost 19 hours. So the separation is, can we say, high, and the spin frequency is 550 Hertz. And the companion spectral type is this one. So these are outbursts, and between outbursts, this source shows outbursts almost each year. Okay, so when you zoom in this outburst, you see this kind of pattern, an exponential decay, fast rising and exponential decay. And I will come to that in my later slides, but in the decay stage, we see very easily it's made by 2 different slopes, which is called slow decay and fast decay stage. Okay, and you can feel something like there's a knee between them. Okay, so I will come to that again. And it's also classified as accreting millisecond X-ray pulsars. Maybe students are not very familiar, but some of you can be. Low mass X-ray binaries, most of the low mass X-ray binaries do not show pulsations. If they show pulsations, they are classified as accreting millisecond X-ray pulsars. And some of them are intermittent AMXPs, which shows pulsations only for limited period of their entire observation period. So this source is quite interesting source, and actually people spend their life to get some pulsations from Aquila X1. But it showed pulsations only for 150 seconds duration over more than 20 years of observation. So that's 150 seconds duration of pulsation makes this source accreting millisecond X-ray pulsar. So it's really worth to work on. But as I showed the constraints of Insight HXMT, unfortunately we couldn't observe and we couldn't cover all the 2018 outburst. Actually, we could start from here, but because of the solar avoidance, we couldn't start the observation, and we have only 3 data there. As I said, this is very early stage of Insight HXMT, and we were quite motivated to get some signs from the data of Insight HXMT. And this was very interesting source. It was in our observation list, and we were waiting it will turn to an outburst, but unfortunately we couldn't observe because of solar avoidance. So we observed at here. It was very faint, especially for Insight HXMT. Actually, the observation team of HXMT has 100 criteria to start an observation. Of course, if it is an important observation, that criteria can be lower to start. So finally, we have 3 data here. Okay. So then we asked ourselves if it is worth to work on or not. And we wanted to know what conditions of that star has, what physical conditions that system has in those times. So because it seems like it's just in the transition from decay stage to quiescence. It was very faint. And at that time, actually, I applied a method which is invented by me and my supervisor, Professor Yavuz Ekşi. So I will just spend a few slides to introduce you this method. The method is based on to describe light curve from another window. Okay, so light curve is time versus flux, count rate to luminosity. So it's basically changing brightness in time. So this has a unit, this also has a unit. So you cannot compare exactly this outburst with this outburst because these outbursts has different powers of flux. So to better make a comparison between 2 different outbursts, we wanted to make a unitless space to have a view of outburst. And so let me spend a few times on this slide. So what happens here? As I told, there's a neutron star at the center and there's an accretion disk around it. So according to the location of the inner layers of the disk, accretion starts and the mass rotating in the inner layers of the disk moves to the surface of the neutron star. So basically, if a location of the neutron star is inner than a very specific location, so-called corrotation radius, but I will not give all the details of the model here, but if that inner radius is closer to the star, then accretion starts. So this is what we see here. This is the accretion. Okay, so the energy that we see, the luminosity, the X-ray luminosity that we observe is the gravitational potential energy of inflowing material. So if we define m dot star, which is mass transferring onto the star per unit time, is given with this equation. So we can just throw these out. This can be constant. So it's directly related with m dot. Then this evolution is also giving us the evolution of mass transferring ratio onto the neutron star. Okay, so if we can get a time evolution from here with this function, actually I used this function, this it's a decay function, and this tau is the decay rate. This tau is the time scale of the outburst, and this alpha is the decay rate of the outburst. So if we can represent this decay with this function, we can also get the time evolution of inflowing mass ratio to the neutron star. In some papers, this Ni is called, is actually linked with the transition between accretion stage to propeller stage. So now I say one thing else, which is propeller stage. So as I told you, the inner layers loses material and it starts to shrink back. It's something like water waves. So it comes to the neutron star, it becomes closer and it loses the material and it starts to shrink back. and it passes that specific radius again while the inner layers of the disk shrinks back. So when it passes from that specific radius is linked to this knee. So this can be the transition from accretion stage to propeller stage. In the propeller stage, actually, propeller effects, the centrifuge barrier is also affected. So it just distributes the matter to outside. Then we don't see all the materials moving to inner layers of the disk, transfers to the neutron stars. But a ratio of it can. So if we can define here the slow decay stage with a function, and if we can extrapolate this to here, the ratio between this line to the extrapolation of this line will give us the mass ratio of inflowing material, the mass ratio transferring to the star as a unit of inflowing material, reaching material to the inner layers of the disk. Okay, so it's something like mass comes from outer layers to the inner layers of the disk, and as a location of the inner radius of the disk, that mass transferred to the neutron stars. Okay, so here just a portion of it can reach to the neutron star. And by using this formula, we can make a unitless parameter, which is F, and all is obtained by luminosity. So now we can convert this y-axis, which has a unit, to a unitless y-axis, which is F. So then these outbursts are comparable right now. Okay? So, but what about the duration? So we should do something for duration as well, and we should obtain one more quantity for duration. And because outbursts can have different duration, for Aquila X1 case, it can be 30 days up to 100 days. So for also x-axis, there is one more parameter, which is called fastness parameter. I will not give all the details of the model, but this is all done to understand where we observed Aquila X1 by Insight HXMT. Okay, so now I'm trying to understand the data first, and then I will analyze the data if it works to do, and I will use some models to describe the physics there. Okay, so I'm just trying to understand what physics is behind that data. So the fastness parameter is a ratio of angular velocity of the star to the Keplerian angular velocity of inner disk radius. So it's given as this. It's a ratio of this one, the co-rotation radius. So I will not give all these details, but fastness parameter can be written as this. This L critical is the luminosity of here. By the way, how many minutes do I have more?
5 minutes.
5 minutes. Okay, I will finish in my 5 minutes. No problem.
Okay.
So this also depends on time, and this F also depends on time. So now we have two parameters, both unitless, both depends on time. So we can make a parametric plot of outburst, fastness, mass ratio, the F parameter versus fastness parameter. Okay, so what do we expect actually? What we expect is before the co-rotation, before the inner layers reach the co-rotation radius, all of the material will reach to the neutron star. Then all of the material, the ratio is 1. Okay, so after the co-rotation radius, for the ideal case, none of the material will fall on the neutron star. Then this function, this F versus fastness parameters, must be a step function. Okay, it can be a step function. This is a step function. But of course, in a real world, it also depends on thickness of the disk, etc. In a real world, we never see that kind of step function, but it will be a smoothed step function. So this is a smoothed step function. Okay, we can use tangent hyperbolic for step function, and this part makes it smoothed step function. And we have two functions. This ft is smoothed step function, and this represents the slow decay stage. And now, multiplying these two, we can represent all of the decay, both slow decay stage and fast decay stage. So in this picture, actually, we have done this for almost all outbursts of Aquila X1, but we have published this in far before. I'm just using this model to understand where our HXMT data is. So after I have seen this picture, okay, now it's worth to work on it, because these data are still in the propeller stage. Okay, so now we know what physics behind that. So the inner layers of the disk around co-rotation radius, maybe it's a bit outside, but a portion of the material reaching inner layers falls on the neutron star. Then it's worth to work on it. So this is the hardness ratio, and hardness ratio gives us the state transition. Of course, the error bars are huge, but still we can see some trend, and the data is just after that transition. Okay, so after that, we started to analyze the data. And at that time, actually, a high energy detector, the calibration of high energy detector was not well finished. So I decided to use only low energy detector and medium energy detector. Sorry. Because in my previous papers, I also used RxD PCA data, which is sensitive from 3 kV to 30 kV. By using LE and ME, the spectrum will be comparable to the RxD PCA comparable, and I will be able to use my previous knowledge, previous experience on this. So I modeled this spectra by using few different models, and I saw the most reliable model is this black body, and a quantization model. In RxD PCA data, actually a Gaussian line was necessary, but here we couldn't see any Gaussian line is necessary, and this was the spectra that I obtained. So I used few models, and these are three data. In model one is black body just power law, and this black body adding quantization only to black body and adding quantization only to this black body, but still the most reliable model is called model 5, has these parameters. So we also published this in Journal of High Energy Astrophysics with hundreds of authors. And I will just want to give my final remarks especially for the 4th generation researchers of Turkey, for the young generations who will be my students. Insight HXMT is an ongoing mission. So there are data there. And the people in IHAB are very motivated for collaborations. So go and get the data. And there are also public data, so you can just obtain. And on August, I think the 4th term for applying proposals will start, so you can also apply with a proposal. Thanks for listening. It was very special for me to give a talk organized by Ege University and Istanbul University. So if there is any question, I can try to answer. So that's from the equation.
And we thank Dr. Can GÜNGÖR for his nice talk on HXMT observations and modeling. Sorry, but we have no time for questions and we need to move to the next speaker. If there's any question to GÜNGÖR, I see two in the chat panel. You can read and answer from the chat panels. Now we need to move to the next speaker, who is Dr. Erbil Gügercinoğlu from Sabancı University, and Dr.